don't have a ton of time today, but I know we also had sort of partial attendance on Tuesday. And I think this is an important enough topic that I want to make sure everyone is in the same place with regards to what we are doing in Lab 4. That's another lab where parts of it just seem like you're just typing in commands and things kind of sort of work. And it has to do with this broader topic of escalation, of gaining additional access to the system that you already have some access to. And we were getting around to the point of how one can go about cracking passwords and by what nature that works in practice. And I think it's pretty cool technology, and I want to make sure we cover it properly. And it started the very basic background. We talked briefly on Tuesday, I'm going to bring it up now, this concept of hash functions, and we'll talk today about how it relates to passwords. So again, as a sort of a review of Tuesday, hash functions, you'll also hear the term one-way function, or you'll also hear the term message digest. They're generally referring to the same thing. The idea is you have these functions that take a relatively large amount of data, here represented as being m bits of data, and they apply some usually arithmetic style function to it to generate a fixed length output. That is the h bits, that is the actual hash result or the digest of that function. The concept behind them is that if you've designed a quote unquote good hash function, if you have any even small changes in the input, it's going to correspond to relatively large changes in the output. So in some sense, it's a way of checking if your data has been modified. As we'll see, it has other purposes as well here. We brought up Jenkins hash just as an example hash function, and not necessarily a good one, but one that's been in use in many different contexts over the years. And my point about the source code for that in C was that, well, first off, it maybe looks a little bit different than C source code you may have used because it's a lot of just low-level arithmetic that you may or may not do in your actual coding practice. Things like additions, shift operators, and XOR operators and the like are what you're going to see. Digital logic style bitwise operators are what you are going to see in those hash function implementations. And I actually implemented this and provided a few different input strings to show that quote unquote good property of this hash function, for which we have 3 input messages. In this case, they're all the same length, but they don't need to be. They just need to be of some length, typically larger than the hash value itself. And so it could be a whole paragraph, could be a whole book of text, could be a whole 15 gigabyte distribution of an operating system. And as that function gets applied to them, we wind up with 3 different 32-bit outputs, and significantly different ones, right? We change the input, in this case, by a single byte, by a single ASCII character. It's probably 2 to 3 bits from E to I to A in that change, yet the result is going to be quite different. And I think there's a little bit of just, trial and error or just explore through practice with that, because at least for me, it is hard to look at the code for that hash function and feel really confident why it results in a relatively good hash function. Why are we shifting to the left by 10 and then after we do an XOR shifting to the right by 6? I don't know. Why not 7 bits? Why not 8 bits? They all tend to have that sort of flavor to them. There are then those who apply sort of more of a rigorous mathematical theory in the design of hash functions and the like to have more provable properties of that kind of confusion of input into our output. But by their very nature, because we are taking m bits, where m can be quite large, and we're producing an h-bit output where h is going to be relatively small, and it's going to be a fixed small, 32 bits, 64 bits, 128 bits, something like that will be the output. By that very nature, there are going to be so-called collisions, which is to say you'll have all sorts of different outputs, and mathematically it's guaranteed to happen, that will result in the same hash output. That's just the nature of trying to take too many possible inputs and combine them all into a very relatively small set of outputs here. In this case, I just kind of ran a bunch of different strings until I got a result that matched, and it didn't take very long at all. There's nothing special about this string other than when you throw it through the same exact mathematical function here and you run the same C code upon it, you wind up getting a collision with that input, and they just correspond to the same value. That is not a flaw per se. That is sort of a byproduct of the very nature of a one-way function. We go from many possible inputs to relatively few number of possible outputs, and consequently there's going to be all sorts of inputs, and we can calculate the exact number, but there's going to be all sorts of inputs, different inputs, that are going to lead to the same exact output. What makes a hash function good or bad, depending on the use case, is a matter of how easy is it to find one of these other inputs that is going to match your existing inputs hash output. Because it turns out for some of these purposes, if it's relatively easy to find an input that matches the exact hash function you're already interested in, well, then we can do some more deceptive things with regards to passwords or distributing software or these other use cases of hash functions. Hashing looks a little bit like encryption, and the source code also looks kind of bit like how encryption source code tends to look. It is not the same, although they are related concepts in terms of what we are trying to do with our input. They're not all used for security applications. If you've ever used something that required a cyclic redundancy check, the determination of what the last digit of your credit card needs to be based on the first 15 or so digits, or the last digit of a barcode based on the prior digits, that's effectively also a hash function. It's just a way to quickly check that all the previous values that I transmit, was there any loss along the way? And it's just a quick little sanity check of, we run this mathematical algorithm on those previous 15 digits. This is what we expect the 16-digit needs to be. And if it's not that, well, then something happened. We lost a digit, something got modified along the way. And programming languages that provide things like dictionary data structures, right? Where you can look up a value in this dictionary you can look up a variable by value, also use hash functions for that purposes to avoid having to do just a linear search of a larger data structure. Instead, it calculates the hashes of those variables and determines if that hash is already existing in the data structure. If you want to look at how Python does it, CPython is still by and large how people execute Python these days. In pyhash.c, it's exactly the hash function that all the Python code you would run is using underneath the hood. And it's kind of interesting. I mean, it's interesting in the sense of, to me, it doesn't really look that much different than the Jenkins hash. The trade-off is oftentimes in terms of the randomness kind of properties of the hash result versus the resulting performance of it. In this case, because it's a hash not just for arbitrary input data, but it's a hash for data structures, they apply slightly different hash approaches depending on the actual value of the type of the variable that is being processed here. So there's pi hash double, for instance, that takes a double and it checks if it's infinite, and then there's it has some constant value provides for that. And then it looks a little magic here. We don't need to go through the entire algorithm for what pi hash is doing, but it's really not that different from what our Jenkins hash is doing. Do a little bit of arithmetic modification of it, return back kind of a modulo value back that is then going to be the corresponding part of the hash for that part of the data structure. And it applies that hash functions. If it's a pointer, it applies a hash function. If it's a buffer, it applies a hash function. And that looks quite a bit like a Jenkins hash there as well. And for different types of variables, it will return different values for the hash function. That's just another example of what a hash function can be used for. We then refer to sort of non-cryptographic and cryptographic hash functions. What makes something a so-called non-cryptographic hash function is it does not attempt to make any real sort of rigorous guarantees about how hard it is to do what we showed here, how hard it is to generate two identical hashes for the different input types that we have here. By contrast, when we have something that's referred to as a cryptographic hash function, they are intended for security-related applications and attempt to provide certain guarantees. The thought is that if a malicious adversary does any modification of the input, they are not supposed to be able to do that without changing what the output hash would be for that changed input. Then this is a little hand-wavy, but if two inputs have the same digest, it should be extremely likely, we'll talk about that in a moment, that they are identical. And then finally, a given output should appear to be essentially random here. I showed a picture of hash browns. The word hash kind of predates the concept of hash browns. It just means to mix things up together, to make a hash of things, to just combine a bunch of things together. When you think hash function, think combine a bunch of data together to get a relatively small amount of data back out. So that's a cryptographic hash function. Malicious adversary should not be able to replace or modify the input without changing the hash. If you get the same hash value for two different inputs, they should be very likely to be the same. And then an output by itself should appear to be just random data. But that's a lot of fuzzy language, right? Should not be able to, or is extremely likely, or should be essentially random. Those who work in the field of cryptography Their job, at least those who work in the theoretical side of cryptography, is to provide more of those rigorous, more formal mathematical guarantees. And then kind of on the other side of that same exact coin and really the same mathematical techniques, those who work in cryptanalysis, their job is to attempt to show weaknesses in that theory, to show that certain guarantees were implied by a particular cryptographic hash function, and for these either mathematical reasons or for these just practical reasons as applied in practice, it turns out to not actually be the case when implemented. I don't know how well you'll be able to read that joke there. This is a very well-known kind of XKCD about the issue where if you can't read that, he says, in a crypto nerd's imagination, his laptop's encrypted, let's build $1 million cluster to crack it. No good, it's 40,096-bit RSA. And then what would actually happen in practice is you hit him with this $5 wrench until he tells us the password. And you can Google the term rubber hose attack, which is kind of considering security in the presence of like real physical danger, that you can have all the world's best cryptographic functions for hashing and for other things, and can it withstand kind of the physical pressure to provide those secrets, even if logically those things can't be broken. And with regards to all cryptography, these hash functions are really no different. It's a little bit of an arms race in the sense that these things get proposed, they become in wide use, and then one of two things then tends to happen. Either the theory side tends to advance, and we do eventually as a field develop more theory that shows we believe that this kind of analysis wasn't possible, and it turns out it actually is to some extent. So there tends to be then theoretical attacks against a cryptographic cipher or against a hash function. And then what also happens is just the advancement of computing technology. What was considered to take 10 years, in let's say 1992, can now be done in 10 seconds today, right? And so the assumptions that were made at the time of creation are no longer as true as they were. And so you do see this evolution in the cryptographic space just by necessity. So you will still see the MD5 hash function used quite a bit, but it's quite convincingly been sort of cryptographically broken. Again, the algorithm for this is kind of the more mathematical view of the same logical and arithmetic operations. It turns out, due to its creation, and this was from 1992, here's the kind of pseudocode for it, it turns out that now in practice, it is quite simple to do that sort of chosen collision attack, that if you have something that you're sending along with an MD5 based hash, it is relatively easy for an attacker today to create a different input that would then instead have the same exact hash. And that's considered broken in this context. But it's not exactly a binary thing. You will still see MD5s used as checksums for all sorts of purpose. The thought being in those contexts that yes, an attacker who perhaps intercepts the input and the checksum could create a different input with the same exact checksum, but depending on what's being distributed via that hashing mechanism, the thought is they can create something, but it's much harder to create something valid and malicious that would have the same checksum. Today, it's more likely in these contexts you'd be using one version of the secure hash algorithm, which are still very much in development. They are quite similar to each other. They're just iterative versions of that same kind of arithmetic and logical processing that's performed upon the inputs, with different trade-offs in terms of the amount of time they take to compute and the perceived strength from a cryptographic perspective of the resulting hash that gets generated here. From our perspective, why I bring up this introduction in the first place, and we will continue this next week as well, is a very common use of these cryptographic hash functions is to hash user passwords. The idea being, when a user provides an input, we're going to perform that hash computation, and we're going to check the hash values of that input password against the stored password versus actually storing the passwords themselves. I guess if this point isn't clear, then the rest of this isn't going to make a lot of sense either. So you have a password, perhaps it's Hunter2 or something, and that this is quite old, but it still makes me giggle. Say your password is Hunter2. It has long been part of secure system design, the assumption that that is your password. We do not want to actually store Hunter2, that string, anywhere in the resulting system. You are typing it in. The system is going to check if you have typed in the password correctly. Instead of doing, what do you want to call it, a string comparison of password to password, we instead have a pre-computed hash of the known correct password. We then compute the same hash function on your input password, and that is what we're checking against each other. Under the assumption that, as we talked about, if there are inputs that are different, they are extremely likely to have different hash results as well, but not mathematically guaranteed to have different hash results, because as we talked about, there's still that fundamental limitation. You have a certain input where m can be potentially quite large. You have a resulting hash value h, where h is of some fixed result. There are going to be, in most password-based systems, guarantees that multiple different passwords are going to result in the same hash value that gets stored and compared. But the thought is it's an extremely unlikely one of those, 1 in 10 to the whatever, where that exponent is quite large type of possibilities. So from a practical perspective, not something that we have to necessarily concern ourselves. So common use is in actual password checking and storage. We're going to talk more about this on Tuesday, so come back on Tuesday and we'll jump right back into this then. Okay?